Welcome back, friends. In the previous session we started with discussion of producer-consumer problem, and in that problem we discussed how that concurrently running processes producer and consumer leads to the issue of race condition. To solve the problems of race conditions, which is also I can call it as a data inconsistency or data loss, and the other problem of deadlocks, we need to design some synchronization mechanisms, and the programmer has to use these mechanisms before they access some shared resource. So in this session I am going to discuss the designing aspects of any synchronization mechanism and what are the requirements of these SMs. So let's get started with our discussion. What is the synchronization mechanism? It's nothing but the programming techniques to be used by the programmers when they want to access any resource which is shared among multiple processes. Let's say one process wants to access the data stored at the shared memory, and other process also wants to read or write from that memory. Now these two processes have to make sure that they don't write or read from that memory at one time. They do the reading or writing task or execution of those instructions one after the another and not concurrently. To design the synchronization mechanisms, these terminologies we will need. First term is the critical section. The definition of the critical section is that part of the program where shared resources are accessed. Race condition, we have already discussed in my previous sessions how producer and consumer leads to the problem of race condition. I'll just summarize here. Two or more concurrently running processes produce different outcomes if their instruction execution sequence is changed. So in ideal case, we don't want this race condition. The third term is preemption. Since the start of this course, I am talking about this preemption, which is nothing but forcefully halting the execution of the running process and shift that process to ready state and schedule any other process to CPU. The fourth term is principle of mutual exclusion. What it means, no two or more processes executing the code of critical section simultaneously. To better understand the critical section and the principle of mutual exclusion, let me take these programs. Here I have again taken the producer program and consumer program. So as n, buffer and count, these are the three variables shared by producer and consumer. The lines of code at which these variables are used, I can call those lines of code as my critical section. So in the producer I can see at this statement where I am checking the condition while this is the busy waiting statement. This statement I can call as a critical section statement. The next statement is buffer. So these both statements I can call as my critical section statements, or in simple words, critical section. And next statement is using the mod n. So n is also shared, but n is a constant value which is hash defined. So if you call it as a critical section or not, it will not matter. But definitely count is equal to count plus 1 is going to modify the value of count, and that's why I have to call this statement as critical section statement. Similarly, in the consumer, these two statements are using the common variables, global variables I would say, or shared variables. And again, count is equal to count minus 1. Modifying the value of count, I can call this statement as well the critical section. So whenever you write any program, as a programmer, you first needs to identify your critical section instructions or statements. Let's talk about the principle of mutual exclusion. Let me take these two programs, P1 and P2, and a shared variable count. A, B, C, D are the local variables to P1. So first operation is A is equal to 10. This operation, this execution is on the local variable. That's why we don't have to call this as critical section statement, or I don't have to think about the race condition occurred in modifying or accessing the value of A, because A is a local variable. So here I can see count is used in this statement and the below statement count minus minus. So these two statements I can call as critical section statements. And one more statement, that is printf count, is reading the value of count. I can call it as a critical section. Similarly in P2 I have count used in these two statements and as well as the printf statement. So first we identified the critical section, and now the principle of mutual exclusion says that if the process 1 starts the execution, let me start the execution by indicating the program counter here. Let's go ahead. The moment this program counter reaches this statement, just before the critical section, this process have to make sure that no other process is executing the code of critical section. So here as of now, there is process P2 which is not yet started, I can say. That's why this is the only process and it can go further. While it is executing the code of critical section, now assume that the process P2 arrives. It starts its execution of non-critical section code. Now it reaches to a point where it wants to enter into critical section. Now as at this moment, P1 is already in the critical section. So the technical meaning of having the process in the critical section is nothing but the program counter of that process is set to one of the instruction in the critical section statements. So therefore, this process P2 must have to wait here. Till when? Till the process 1 comes out of the critical section. So let's go ahead, and P1 now comes out of the critical section. The moment it comes out of the critical section, according to principle of mutual exclusion, this process can now continue and enter into the critical section. While it is doing the execution in critical section, the other process, which is P1, can execute the non-critical section. Now here again process P1 wants to enter in CS, but P2 is already in CS. So that's why we have to make sure that only P2 will execute further and P1 will wait here. So let me proceed with P2. It will come out of the critical section now. The moment it has come out of critical section, the process P1 now can enter in critical section. And now P1, assume that it has reached to the end of the function, and now P2 can continue. It can enter in CS because P1 has already passed all the CS, and it can exit the critical section, means come out of the critical section and complete its execution. So in this demonstration, you must have observed that at any given point, either P1 enters in critical section or P2 enters in critical section. So that is, we call it as a principle of mutual exclusion. Let us discuss now what are the designing aspects of the synchronization mechanisms. As a programmer, you need to design two things in the synchronization mechanism. First one is called as entry section and the other one is called as exit section. Let me take this diagram. Assume that I have written some critical section code, just showing in a block diagram, and there are 3 processes wants to enter in their critical section. Now before entering in critical section, we will put some code. That code I will call it as a entry section code, which will make sure that only one process is allowed to go further and enter into critical section. Other process will wait here. So if I assume that P1 as the critical section, can I enter in critical section? Entry section says that you are the first one to arrive. Now go ahead. So let's assume that the P1 is here in the critical section. While it is in the critical section, P2 arrives. So P2 will wait here in the entry section. So that's how we have to design this entry section. Entry section should know if anybody has already passed through the entry section. So other process, if it comes, entry section will make that process wait. Assume that process P2 and P3 are waiting in the entry section now. Now, while they are waiting in entry section, let's assume that the process P1 completes the execution of CS and comes below in the exit section now. Now, after the critical section, we have to put some piece of code, that is exit section code, which will make sure that if some other process is waiting in the entry section, here P2 and P3, then P1 needs to make sure that those other processes waiting in entry section, one of them will be unblocked or its wait will be over, and one of the P2 and P3 only will enter in critical section. So that's how, with the help of this entry section code and exit section code, I achieve the principle of mutual exclusion. Let us discuss what are the requirements for designing any synchronization mechanism. The first one is the mutual exclusion that we just discussed. That principle of mutual exclusion must be guaranteed by your entry section mechanism. Let me explain this with the help of this C++ example here. So I take two processes P1 and P2. Here I have some piece of code, let's assume, which is non-critical section code, and here is the count, which is a shared variable. So I marked these two statements as critical section statements. Here also in P2 I have some critical section. Now what is a synchronization mechanism is, I have to put some piece of code before the critical section in both the processes, or I can say in both the programs, or I can say in both the functions. And these entry section code makes sure that no other process has entered in CS, and then only this entry section will allow the entry in the critical section. Similarly, as I said earlier also, we have to put some code below the critical section, and this section will make sure that if any other process is waiting, then unblock that process or send some kind of signal to that process that my job is done, now you go ahead. Let me take the program counter here, which starts the execution of P1. So it has first executed some non-critical section code, and now it reached to entry section code. This code, by the way, we have to design now. That's what we are going to learn in the next sessions. Now this program, the moment this program counter reaches entry section, this code will make sure that no other process has passed, means went through their entry section code. So as of now, there is only one process I have taken, started the execution of P1. So this is the first one asking the critical entry section that, can I enter into CS? Now since nobody means process P2 hasn't started it, I can say that this entry section code allows this process P1 to enter in CS. Now while the program counter is set inside the critical section, let's start the execution of process P2. Now here the entry section of P2 will say that the process P1 has already passed its entry section and it is executing the code of its critical section. So you have to wait here. So that's how the entry section of process P2 will make sure that this program counter will not proceed in the critical section code. It will stuck here or it will wait here. Now here, let me continue with process P1. It comes out of the critical section, and this exit section now makes sure that the wait for the process P2 is over, and now process P2 can go further and enter in its critical section. After some time, it comes out of the critical section and executes the exit section code. So that's how the general design of the any synchronization mechanism. Just to summarize, before critical, first identify the critical section statements. Before critical section statements, put the code of entry section code, and after the critical section statements, put the exit section code. And that's how we can achieve the mutual exclusion with the help of this synchronization mechanism. The second requirement is called as progress. Before I talk technically, let me give you the analogy. Let's assume that there is a room which is empty, no one is in the room, and outside the door there is a gatekeeper. And there are several, assume that these are the 4 students with the roll number 1, 2, 3 and 4, which are interested to enter in this room. Now one of these students comes ahead and asks the gatekeeper, "Can I enter into the room?" Gatekeeper says that, "Yes, there is nobody in the room. You go ahead." So if the answer given by the gatekeeper is yes, you can go ahead, then I say that progress is guaranteed, because any random person that comes ahead first, out of these 4, if any random person comes ahead first and gatekeeper just sees if the critical section is free, that means here room is free, allow that person to enter. In that case, we say that the progress is guaranteed. Let's assume that there is another case where gatekeeper has implemented some other algorithm, other rules for allowing the people to enter into the room. The rules it applies is the entry in this room will be only permitted according to the roll number of student, starting with roll number 1 only. If it implements this algorithm at the gate by the gatekeeper, then even if this third person or third student comes first, then gatekeeper will say that, "No, you are not allowed to enter into the room." Why? Because as per my rule book, I am supposed to give the entry to the student with the roll number 1 first, and then only student 2, afterward you will get the entry. So here the situation is, even if the room is empty and this student with the roll number 3 comes first, gatekeeper disallows the entry, and in this case I can say that this system or these algorithms implemented by the gatekeeper does not guarantee progress of the processes. Talking about the processes and critical section now, if any process that comes first and asks the entry section, here gatekeeper is like entry section, and asks the entry section that, "Can I enter into my critical section?" If the entry section says that, "No, you cannot enter," even if critical section is free, then in that case we say that progress is not guaranteed. Let me summarize the progress one more time. If there is no process in the critical section, then any process which is willing to enter in CS should be allowed to enter. Also, the second condition in the progress says that there should not be any deadlock among these processes which are willing to enter in CS. So in short, it should not happen that the processes are fighting with each other. There is some faulty program we have written in the entry section, because of which the situation has arisen that critical section is free, no one is in the critical section, and though the two processes are waiting for each other for some infinite time to get the entry in CS. So we should not have a program or the logic of entry section in which there is a possibility of deadlock among the processes. I'll explain progresses for each and every synchronization mechanism that we are going to discuss further also. So how to check programmatically if progress is guaranteed or not for the given set of programs. Let's say if you are given two sets of program, process 1 program and process 2's program, and you are asked the question, if these two processes run concurrently, does they guarantee progress or not? So the steps you have to follow is, first consider that only one process out of these given n processes, here I have taken two processes, arrives. Check for that first process if it is able to enter in CS. Remember that don't start the process P2 as of now. Just start the process, first process P1 I would say, and let it go ahead, and it should get the answer from the entry section that yes, you are the first one, go ahead in the critical section. And this you have to repeat. This question you have to ask for each and every process, assuming that it has arrived first. If the answer is yes for every process out of n processes, then I can say that this synchronization mechanism guarantees progress condition. The third requirement is called as bounded waiting. So before I explain the bounded waiting, let me give this analogy. One more time, let's take this example of empty room where I have the gatekeeper. And these are the 4 students willing to enter into this room. Now this student number 3 comes ahead and asks the gatekeeper, can I enter in the room? The gatekeeper says that yes, you are the first one and the room is also empty. Go ahead. After some time, when the student number 3 is in the room and utilizing the resource, the other student with the roll number 2 comes ahead and asks the gatekeeper, can I enter into the room? This time gatekeeper says that no, you have to wait because there is someone already in the room. So here student 2 starts waiting. Now the person in the room comes out of the room and asks the gatekeeper one more time, can I enter again? This time gatekeeper says that yes, go ahead because the room is empty. At this moment, student 2 is waiting and student 3 has asked again to the gatekeeper, can I enter? Gatekeeper simply look at the room and says that the room is empty, you go ahead. If the gatekeeper allows this student 3 to enter again, in this case, the student 2 says that it is not fair with me because I am still waiting here and you have allowed, that is the gatekeeper has allowed the entry to this person, that is student 3, 2 times. So in this case I say that the bounded waiting is not guaranteed by this gatekeeper here. In other words, I can say the bounded waiting is not guaranteed by this synchronization mechanism here. In ideal case, we don't want this situation. In idle case, we want this gatekeeper or the entry section of the synchronization mechanism should make sure that if someone is waiting outside the critical section, and if the process which is already in the critical section asks the critical section again, then it should not be allowed. Let me summarize bounded waiting. If a process is coming out of the critical section and asked to enter the same critical section again, then it should only be allowed if there is no other process waiting to enter in CS. Let us now discuss the synchronization mechanism types. The synchronization mechanisms are categorized into two types. One with the busy waiting logic, which is also called as spin lock logic, and other one with the blocking logic. Let me first talk about the busy waiting logic. Busy waiting is nothing but programmatically checking some condition in some loop till that loop breaks. Earlier also I have written the while loop in producer consumer problem, which was the busy waiting statement. Whereas in the blocking mechanisms, the program is going to check some condition only once, and depending on that condition is true or false, this OS is going to put that process in the block state. So in this case, the condition is going to be evaluated only once, and outcome of the condition decides whether that process is going to be blocked or whether that process is going to be allowed to do the further execution. So in busy waiting, process keeps on jumping between running and ready states. So here, let's say process P1, critical section is, let's say, is not free, and some process, let's say process P1 arrives. Process P1 is scheduled to CPU. It's in the running state. In the running state, it will check the while condition, the busy waiting condition, if some condition is true or false. Again, it will check if that condition is true or false. It will keep on evaluating some condition till that loop breaks. Meanwhile, if the preemption of that process happens in between that checking condition, then that process will go to the ready state. And again, after some time, if P1 is scheduled, again it will continue checking that condition. So here, the busy waiting is going to jump from running to ready and ready to running state. Whereas with the blocking solution, the process is moved to the block state. So here we learned state transition diagram. Let's say the P1 is here in the running state and it wants to execute some critical section code. But before, in the entry section, I am going to check some condition. And that condition says that no critical section is not free. You cannot go ahead and execute your code of critical section. So it will ask the OS that let me go in the block or wait state, and whenever the critical section will become available, means no one will be there in the critical section, you just wake me up and that process will come to the ready state now. And eventually after some time it will get to the running state and execute the further code in the critical section. So here the block or wait state is also involved in the blocking mechanisms. The difference between these two mechanisms is, in the busy waiting mechanisms, the CPU is extensively used in evaluation of this condition in the some loop. Whereas in the blocking, only few CPU cycles are required for evaluation of condition only once. And then the OS decides whether to allow that process to enter in CS or to just block that process and move it to the block state. Once the process is moved to the block state, it will not consume the CPU, and nor the CPU scheduling algorithm is going to consider that process, because CPU scheduling algorithm runs only on the processes in ready state. And here I am going to move the process in the block state till someone wakes that process up. Now let me tell you the standard synchronization mechanisms that we are going to discuss. These all mechanisms are categorized into three types. First one is the software type of mechanism, which is implemented at user mode. Means you can write simple C, C++, any higher level language programs for implementation of these mechanisms. There are three mechanisms that we are going to discuss. First one is called as lock variable. Second one is called as strict alternation. And the third one, and very popular, is called as Peterson's solution. The second category is hardware-based solutions. To implement this solution, we have to make sure that CPU provides some privileged instructions. For example, there are two privileged instructions. One is called as test and set lock, stands for TSL, and other is the swap instruction, which swaps the value of two variables. So until these instructions are supported by CPU, that is hardware, these mechanisms cannot be implemented. So there are the hardware-based mechanisms. The third category of synchronization mechanism is OS-based solutions, which are implemented and executed at kernel mode. The semaphore and monitor we are going to discuss, which are implemented by the operating system itself, and user just uses these tools, I would say, or these mechanisms in their programs at the user level. Execution is done at the kernel level whenever the user level program is going to invoke these mechanisms. So all these 7 mechanisms we are going to discuss one by one from the next session. So with this discussion, I conclude this session here. We discussed the designing and requirements for the synchronization mechanism. And in the next session, I'll be starting with the designing of first synchronization mechanism, which is the simplest among all the mechanisms, which is lock variable. Thank you for attending this session. Have a great day.